It's a very honored to be here to speak in front of you. So first, let me ask a question. How many of you are students? Awesome, not bad. So I have some words to you. So it's very special for me because I graduated from here. And you can guess what happened many years ago. 12 years ago, I was sitting there like you, watching many brilliant scientists speaking about their groundbreaking research. And when I was a student, I was dreaming about doing something like standing here speaking my research as my career. And then today I make it. And now it's your turn. And I really, really hope that many years later, you'll be doing something that you really like as a career. And for achieving that, just start working hard from now. And without further ado, I would like to show you a really good image, one of my best figures. There are 3 panels, 3 colors, showing step-by-step change from the era of labor to the era of automation, and then to the era of AI. You may understand that automation is part of AI. So when we enter the era of automation, we actually already entered the era of AI. But the AI we are talking about mostly today is referring to deep learning. So throughout my talk, I will use AI and deep learning for the same thing. So here, more specifically, we have a frequency magnitude distribution which shows a step-by-step change in terms of magnitude completeness. We go from here, from the red color, from magnitude completeness about 2 to around 1 in the era of automation, and then to around 0.7 in the era of deep learning. So that is the magic it is doing. And remember, this axis is in logarithmic axis. So although they differ not much, they actually differ a lot, by several times. And on the right-hand side, we show a daily distribution about the detectability from manual effort around 7 earthquakes per day to around 70 or 80 earthquakes per day using traditional automation, that is STA-LTA method. And then to the nowadays around 400 earthquake detectability per day, and that's a huge improvement. And on the bottom, we show the magnitude distribution on a daily basis, where we can see that most of the gray dots are very, very small magnitude, all the way down to magnitude around 0. Right? And you may be curious about this particular day. And what happened today is that we had a magnitude 5.4 earthquake on this day, the largest in decades. And we can see that because of this earthquake microscope, we see very, very small earthquake. This very abnormally intense seismicity may indicate the precursor signal of this large event. I'll explain more in my later slides. Before diving into the technical details, I would like to thank a large group of people, current colleagues, former advisors, students, and postdocs who made significant contribution in this work. And without their tireless effort, this presentation is just impossible. And here we have a brief outline of my talk. First, I would like to guide you through a very long journey of putting AI for seismology from infancy to production. And then I will focus a little bit more on the best of the best model, our EQCCT model, which we really put it in our daily operation. And then I will introduce some really important sensitivity tests and some real-world application of this method. And then later on the other hand, I will introduce several AI applications showing that how the best techniques can help us do better science. First of all, I'd like to state the problem. The problem we are solving right now is really to pick the P wave and S wave from the 3 component seismogram. And to do that, we can use the traditional method, the STA-LTA, representing short-term average, long-term average ratio. And we can use clustering method, and we can also use very advanced deep learning method. All we need to do is to pick the P wave and S wave. And all the follow-up steps are integrated very seamlessly. so that we can output catalog very beautifully. But the most critical part for the whole framework is this picking, P wave and S wave. This is the only step that requires human interference. And all my talk is about how to pick this P wave and S wave as accurate as possible. The current ongoing AI booms really started in early 2016. On that particular day, probably you still remember this picture. On that particular day, the company DeepMind made a stir by announcing that their AI player beat the best human player for the first time. And then that AI player is called AlphaGo. And that news really ignited the curiosity of the whole world, including me. At that time, I was a distinguished postdoc at Oak Ridge National Lab, and we were doing a very ambitious project. We want to invert the whole Earth's interior structure using full waveform inversion, using thousands of earthquakes. And the principle of full waveform inversion is to iteratively update the current Earth model so that we can best fit observed data. Right? And the problem for this process is data preconditioning, because we want to scale it up to 5,000 magnitude about 6 earthquakes. So that's a huge amount of calculation, huge amount of work. We need to make the whole process automatic. And then to make it automatic, we need to carefully select the waveforms that we have the close observed data and synthetic data. Right? And then that problem brought me to the field of AI. And my initial idea was to think about several features, more or less related with the closeness between synthetic and the real earthquake data. And I defined these 5 features, physics-based features, and then I used a very straightforward feed-forward neural network with input as the input training sample is the previously defined features, and output the predicted value, which is waveform or not waveform. With this simple, straightforward neural network model, we actually did a pretty good job. Back in the day, we really didn't have many resources for earthquake detection. All we have is Python and NumPy. So I had to write a package from scratch. So here is an example showing a screenshot of the package I wrote at that time. You can see the first commit happened around 8 years ago. And on the right-hand side, I show an example of the neural network earthquake detection class I wrote for my first package. And when we applied it to real earthquake data, it actually did a pretty good job. And to the extent that it's even better, a little better than the state-of-the-art, that is a flexible method. For some areas like this, we detect previously missed waveforms. And for methodological development, we always want to be more ambitious. We want to develop better and better approach. And this approach, the very initial trial, things work. But the disadvantage is that it requires the synthetic data. But generating synthetic data is not trivial, right? It requires, for such scale, it requires HPC and requires a lot of other resources, and it's not generalizable. To make it generalizable, we need to be synthetic data free. And then we come up with the idea of using clustering. So the idea of clustering is to define a number of features. And then we group the samples into different classes with closest distance in terms of these features. For example, in this case, we define 3 features. One feature is the ST-LTA, which is the traditional criteria to pick the arrival. But we can see that the ST-LTA feature is quite sensitive to noise, right? For these very simple waveforms, we have quite a number of peaks. But if we include other features like mean, like power, we can certainly include other features. And then we can make a a better decision. For example, for this example using STA-LTA, we thought this is the arrival, which is obviously wrong, but using clustering method, we pick it correctly. And we also want to extract waveforms so that we can do application like time reversal imaging or waveform-based imaging and inversion. Instead of using STA-LTA feature, which is quite sensitive to the arrival information, we use the spectral centroid feature, which is more sensitive to the waveform information. And we use the same framework, and we detect those waveforms from very noisy data successfully and automatically. And we can see an example here, and this is a zoomed figure. And when doing time reversal imaging to locate the earthquake source, we found that these carefully selected waveforms get the image more focused, which indicates a better location. Thanks to the advances of other fields like speech signal processing, we are able to extract more features. For example, in this case, we extract 191 features from the data, different features, mostly physics-based or statistics-based features, 1D feature or 2D features. And based on this large number of features, we can do this job even better. For example, in this case, we have training field data here, we have a label here, and we apply this method to another independent testing field data, and we found these two results. This is from 1D and 2D feature combined classification, and this is by 1D feature only, and we found that both work reasonably well, but including 2D feature make the events smoother and more reasonable. And we also explore the possibility of using convolutional neural network, because this is really the first deep learning trial for our work. Previous trials are just shallow learning or unsupervised clustering method. They are really not deep learning. But for convolutional neural network, we can extract the feature from the data. So the key difference between deep learning and shallow learning are really that for shallow learning, we manually define features, but for deep learning, we automatically extract features from the data itself using convolutional filtering. And in this case, we propose a convolutional neural network-based earthquake detection workflow. And here is a comparison of different methods. First is a very traditional and benchmark state-of-the-art method based on STA-LTA. And in the middle, I show the k-means clustering-based method. We define some features and do clustering. On the right-hand side, we show the CNN-based workflow. We use CNN to first get some candidate waveforms, and then based on the clustering method, we improve the resolution so that we can be a better anti-noise as well as improving the resolution. And this slide really showed the advantage of the CNN-backed approach. In this case, as we increase the noise level, and we can see that the CNN clustering method is the most robust to noise. And probably you've heard the time frequency transform, and which can be used for a lot of applications of deep learning. And this slide really shows the principle of why we can use time frequency transform to improve the performance. So for the same waveforms, we increase the noise level from left to right, and we also calculate the time frequency transform, in this case, a continuous wavelet transform. We see that the signals are mostly the same for the time frequency map, while the noise are mostly residing on the high frequency part. So this is really the principle that why time frequency transform can help us separate signal and the noise better. It has tons of application in different deep learning. And we apply this strategy to the same problem as with detection. We first transform the data to the time frequency transform domain, and then we use 2D convolutional filter to extract many features, and then we use the feed-forward layers to make a decision. As a result, we get an even better and more robust result, as shown in this result. So let's pause a little bit. What's the remaining problem? It seems that we have done quite a lot of work. So what's the remaining problem? And all the models are not bad, but they are not generalizable. what we really need is a very generalizable model, right? But for making the model generalizable, what do we miss in the past research? So the critical thing is the data, right? In the previous cases, we have done a lot of things, but mostly using a tiny, small data set and using a relatively shallow and a simple network. We cannot make it generalizable. And starting from late 2020 and early 2021, we started a more ambitious project. We want to design a very deep network, which we call Scalodeep. So the reason why we call it Scalodeep is, first of all, we use time frequency transform to transform the data to the time frequency domain using continuous wavelet transform with 7 scales. We can use more scales, just a matter of computation. More scales indicate more computation. And here we use 7 scale, and as we can see, it is super deep. And then that's the reason why we call it Scalodeep. And it is the first network that can be generalizable. And for doing that, we compile a data set, the global data set from almost everywhere from the world. And then we apply this model to different data sets around the world. And we found very exciting results. For example, in this case, we apply this model to different cases, like very realistic waveforms. For example, this short duration earthquake, for this very noisy earthquake, and for this waveforms with malfunctioning channel, and then for this long duration earthquake, and for this case, our predicted waveform is even better than the manually prepared labels. And for this case, another malfunctioning label, and this is a seismic event, and this is multiple events in one window. And in this case, we have more malfunctioning channels. For all these cases, the Scalodeep did a very good job. And we need a benchmark so that we understand which method is better. So here we have 6 benchmark results, the methods. And on the background, we see the green one, which is the kind of ground truth of the benchmark catalog. And here we see that 2 methods are obviously better. They are template matching based methods. The reason why they are better because they use prior information, use the template to do the detection. So they are better, but they are not generalizable. For more independent approaches like the Scalodeep method and the CRED method, our proposed Scalodeep method is actually quite better. And if you're familiar with EQ transformer, which is a widely used deep learning earthquake detection approach, this CRED is the very initial version of the EQ transformer method. And then it's obviously better than the STA LTM method for different implementation. And in 2021, the architecture of transformers started to dominate the AI work. And we started to explore its potential in our earthquake detection workflow. So we designed an integrated framework for detecting P-wave information and calculating magnitude estimation, because it's very important for both tasks. As we can see, we have a very complicated network architecture. And here I want to show you just the magnitude calculation performance for the California dataset and for the Texas dataset. And for both cases, we have a very accurate predicted magnitude reviewed by the mean average error about 0.1. For both cases, indicating very accurate magnitude estimation. And here now, you may start asking why all the frameworks are based on P-wave only. Right? The answer is it's for earthquake early warning, because in earthquake early warning, we want to distribute an alert for people to take immediate action to save lives before the most destructive earthquake hit the ground. So every second matters in earthquake early warning. And also the time difference between P-wave and S-wave can be up to 20 seconds. So every second matter, we really are allowed to use P-wave information. But for earthquake early warning, we also need to provide the location information so that we can calculate the PGA, PGV, peak ground acceleration and velocity. And we propose a ML-based location framework based on random forest architecture. And we propose a workflow in two cases. One case is where we have a very large training database, like in Japan, in California, and then we can use the real data directly to train a model. And in cases that, like Texas, like Egypt, where we don't have a large amount of data, then we use synthetic data to train a model, and then apply the model to the real data. And this slide shows an application, successful application to a Japanese dataset. So here we show the station distribution, because we have a crazily dense network in Japan, so that we have tons of data to train a model from real data. And these are the training events and testing events distribution. And here we show the location error distribution. Here is the error on the map, and here is the zoomed part, and this is the further zoomed part where we can see very clearly. So what we care is the difference between the red dot and the blue circle. If they are overlapping each other, which means they are correct. This location is correct. And we can see that most cases, they have very close relation, right? So indicating very accurate location. And we can also plot the errors on the map. We see that, very surprisingly, we see the inland areas are mostly low location error, which is because the much higher read density. While in the coastal area, we have a much higher error, which also makes sense because we have a relatively lower read density along these coastal areas. So till now, we have introduced all our attempts for P-wave only based frameworks. So right now, we want to introduce our best of the best model, EQCCT, for daily operation, for picking both P-wave and S-wave. So here are some specs of EQCCT. First of all, CCT represents compact convolutional transformer. And the specialty for this, for our framework, is that we split the P-wave and S-wave training process. So if you are familiar with deep learning, we know that deep learning training process is literally a random process. It's difficult to obtain the best performance for P-wave and S-wave simultaneously. But if we split the training process, it's much easier to get the best performance for both P-wave and S-wave. And on the other hand, actually, we found that P-wave and S-wave are fundamentally different. They have different frequency content, they have different noise levels, so they are supposed to be different. So that's why we completely split the training and architecture for P-wave and S-wave. And it is faster than transform network, and it is better than a convolutional network. That's why it is called compact convolutional transformer. And the big question is why we call it the best of the best model. Because literally we have tried every method we could try, from like feed-forward, shallow learning, to SVM, to a clustering-based unsupervised method, and to different deep learning architecture with different complexity. And I even didn't have time to introduce all these trials. But the key idea is we finally found the best architecture, that is EQCCT, through many trials, many experiments, and many benchmark tests. So here is a clarification why transformer is better than CNN in terms of earthquake detection. So here is an example of face recognition. So for face recognition, all CNN care about is the inclusion of these critical components. If a face contains these critical components, and then it is a face, regardless of their internal relationship. But for transformer, we not only require the inclusion of these critical components, but we need this component to be at the right place. So that's really the key fundamental difference between transformer and CNN. And thus, transformer is better for time series processing, like our earthquake detection problem. And next, I will introduce several real-world applications of this EQCCT model. First of all, I'd like to show you some peaks on waveforms for different cases. For example, for this case, we have a relatively high, large magnitude, higher signal-to-noise ratio. We want to see how the peaks look like compared with the level. And for example, for here, we have P wave and S wave, P wave overlapping with overlapping between the manual one and deep learning one, which really show that it is absolutely accurate. And for the S wave case, we found there's a small shift, and as a matter of fact, this small shift is only 3 samples, so it's still very, very accurate. And the same thing for the other case, even we increase the noise level, we found that those picket arrivals using deep learning are mostly overlapping with the label, right? Meaning they are very accurate. And here is a very noisy case, the same phenomenon. And also, for this case, we also want to demonstrate it is better than all the other alternatives. And so we need a benchmark. And based on the same data set, we compare our EQCCT with the other 2 very famous figures, which are TexNet and EQ transformer. And we can see the arrow decreases from left to right step by step, right, for both P wave and S wave. So this benchmark test really shows the strength of our EQCCT model. And another evaluation is the generalization ability. So we applied to different areas around the world, including Japan, Texas, and Italy. And I will show the results for each case. So this is the picking performance for the Japanese dataset. Right? We can see the P wave, S wave, P wave, S wave, they are very accurate for Japanese dataset. And the same thing happens for Texas dataset. Right? Very accurate P wave and S wave. Right? Slight shift because of the relatively high noise level. And the same thing happened for Italy dataset. And we also do this benchmark test, very specifically showing the error distribution. And from Japan to Texas to Italy, and from EQCCT to TexNet, we see that our EQCCT model is the best among all these alternatives. And the same thing for S-wave. And here we want to test its ability in microseismic data processing. So the significance here is that microseismic data is out of sample from the training database. So in terms of the sampling rate and hydraulic fracturing nature and also geographic location. So one important thing is for sampling rate. So our training database is composed of broadband station, broadband seismic data, which is 100 Hz sampling rate, but for microseismic data, usually the sampling rate is much higher. So in this case, we have 500 Hz versus 100 Hz, which is used in the training database. So in this case, sampling rate is out of sample, and also the training, the triggering mechanism is also out of sample. Most of our training database are from natural earthquakes or induced earthquake from saltwater disposal. So there are really not many hydraulic fracture induced earthquakes. So, but in this case, we surprisingly found that even for this out of sample case, we still did a pretty good job, right, indicating its generalization ability. And here I show a sophisticated workflow from the 3 component waveforms to different catalog, the initial catalog, and then refined catalog, and then the high resolution catalog with different scientific purposes. Now here is application to continuous data, which we already see in the first slide. Here I just skip it. And here is a test, sensitivity test about how the earthquake location algorithm affect the catalog. For example, here when we use a locator with a better velocity, we found that the catalog actually has a higher reliability with better focused events, clusters. So this is also interesting in terms of creating a beautiful catalog. And this is a test about relocation. There are 2 cases. So left one is from manual effort from TexNet, and right one is from AI complete automatic catalog. And the top one show the catalog before relocation, and the bottom one show the catalog after relocation. And we can see that although the initial catalog is not that beautiful, in terms of being scattering, but after relocation, we found a very beautifully delineated fault structure system. Well, it's way better than the TexNet manual effort. And here I show one example of detecting previously missed events. So in this case, it is a very small magnitude, 0.3, and we detected using AI, while this was missed by traditional approaches. And we also show the difference in terms of peaks, comparing the AI and the traditional STA-LTA method. We found that not only the peaks are more accurate, but also we help detect the same event from more stations. Mostly are far-away station and very noisy station. For example, this cyan color denoted station, they are very noisy. We found it using AI while it was missed traditionally. And we also can investigate how the network affects the catalog. For example, if we have much fewer stations, if we only have 8 stations back to 3 years ago, how many events we can detect? And we found that despite a very small number of stations, we can still detect a pretty large number of events. So that really shows the strength of this AI-based workflow. And here we show how the very highly complete catalog can help us to delineate the fault structure, right? And the left is the longitude slice for 3 months, month 1, month 2, month 3. And the right-hand side show the latitude slice, month 1, month 2, month 3. And we see that because of the very tiny and a huge number of small earthquakes, we delineate the fault structure very beautifully. This fault corresponds to the magnitude 5.4 Carlson earthquake. And we can also plot the fault structure on the map, comparing the TexNet, the manual catalog, and our AI catalog. We found that even with 1 month's data, we can delineate those faults very clearly. While traditionally, with very limited number of events, we basically can see nothing very useful. Okay? And also we put this workflow on GitHub, so everyone can download the code, play with the example, and visualize some of the results. And let's pause a little bit. It seems that we have done a lot of work. We have made it really robust in production. And if we want to make it better, so how to make it even better? Considering that it is deep learning, so what we can do is transfer learning. Right? Transfer learning is to fine-tune a model using a regional dataset. But before doing transfer learning, we have to compile the dataset. And then in the past 2024, we compiled a Texas earthquake dataset for AI. And what we do is we compile all the efforts from TexNet Clue, including 300,000 signal waveforms and 200,000 noise waveforms. So here I want to particularly mention that for picking these 200 noise waveforms, I spent 8 months just doing a graphic-based picking and everywhere, on the flight, at the airport, in the restaurant, and on the bed. And so it took 8 months for me to just manually pick these 200,000 noise waves, because it's important, right? We not only need to let the machine to understand the signal feature, we also need the machine to understand the noise feature. So that's really the motivation why we have to construct this large number of noise waveforms. So because of this data set, we can further boost the accuracy of detection. Right? In terms of error, we boosted the error to another level, right? much smaller. And then we even boost the detectability, right? From the previous EQCCT result to nowadays this type of result, right? And we help, because of transfer learning, we help detect the event from very far away station. And also, this is another best figure for me. What we found is, because of this robustness, we have put it in production, right? And here I want to mention the definition of the real time. If we define real time as latency of minutes, we already made it. And if you define the latency as seconds, we are still on the way. But the real-time monitoring will be out this year. And specifically, for this magnitude comparison, we found that for magnitude above 2 earthquakes, we made no mistake, 100% recall. So that's really amazing. And then that is truly the confidence that we can make it in production. And lastly, on the other hand, I want to show several very exciting science examples. So first science example is global adjoint tomography. So because of the AI-backed time window selection, for example, shown here, we can do the largest seismic inversion on this planet. We can invert the whole Earth's structure interior using thousands of earthquakes. Right? So this shows one example using 250 earthquakes. We can see a lot of details, but by using more earthquakes, 1,500 earthquakes, we can see more details. Right? These more details show the deep roots of major geological landscape. And there are still 3,000 earthquakes to go. So we are very looking forward to see next big change for this image. Another example is we can improve the mantle transition zone imaging using SS precursor data. So SS precursor data, as shown by this wave path, it is a reflection of wave. And the beautiful thing is that we can use many reflection seismic techniques for improving this workflow. Right? That's what I'm good at. And what we do is we improve the data quality from this level to this level. Right? And because of this, we recover very high resolution mantle transition zone thickness model. And here is some background story about this project. So there's a region of a famous volcano called Changbai volcano is a mystery. There are some debates. Some debates say that the origin of the volcano is from the upper mantle, and some debates say that the origin is from the deep mantle. And our model showed that we found actually a gap in the mantle transition zone model, and then that explains the origin of this volcano. So our theory is that the hot source material at the very lower mantle can travel through this gap, through this gap to the upper mantle, and finally cause the volcano. And what's more amazing for us is that our AI model even outlines this stagnant slab very clearly, which has never been possible using a tomography method because of the lack of resolution. And another example is to study the earthquake nucleation mechanism. So here is a bit of the background story about this project. So in 2020, we had a large earthquake, magnitude 4.9 earthquake, the largest in a decade at that time. And the difficulty to study this earthquake is very sparse network distribution at that time. And what we do is we use our AI framework to revisit the data, and then found many small aftershocks and foreshocks, and because of that we can explain the triggering mechanism of this of the magnitude 4.9 earthquake. And what we found is right before the magnitude 4.9 earthquake, there was a magnitude 4.0 earthquake, and this 4.0 earthquake caused 11 small magnitude earthquakes down to the magnitude 1. And then these foreshock 4.0 and these much smaller earthquakes, they intricately interact with each other and causing earthquake to earthquake triggering, and then finally trigger this magnitude 4.9 earthquake. And without AI, this mechanism is not possible. And another example is we can study the very intricate relationship between ultra-small earthquake and the injection activity, and also the occurrence of very large earthquake. And by ultra-small earthquake, I mean the earthquake with magnitude all the way down to 0. Right? And we found a very interesting relationship, reverse relationship between injection and seismicity. It's quite counterintuitive because we normally think that more injection causes more earthquakes, but what we found is in the opposite way. More injection correspond to like a quite quiet seismicity, and it supports the delayed earthquake triggering mechanism. And the same thing happened for this case. Because of the earthquake microscope effect, we can see very invisible small earthquake. Traditionally cannot see, and right before the large earthquake, and then it indicates the precursory signal. Right? And another science example is we can study the anthropogenic causal factor of Texas earthquake. So simply speaking, Texas earthquake are generated anthropogenically, not natural earthquakes. What we have developed recently is an AI model that can classify any event into 3 causal factors. The hydraulic fracture cause, shallow saltwater disposal cost, and deep saltwater cost, and the result is shown here. And we see that most of these areas are deeper saltwater disposal cost earthquake. And in these areas, we have mixed hydraulic fracturing and shallow saltwater disposal. And we can verify these results by physics-based method. By physics-based method, I mean we can do temporal spatial correlation between the injection and the seismicity using statistical and physics-based way. And we can say for sure that these results are mostly correct. So that's amazing. Right? And we developed this approach in 2 scenarios, for single station scenario and for multi-station scenario. For single station scenario, we reached an accuracy about 90%, and for multi-station scenario, we reached an accuracy almost 100. So that's really, really amazing. And another science application is an unprecedented fault structure delineation, for example, like this one. And we apply our recently developed AI-based focal mechanism solution. As a geologist, you know what focal mechanisms indicate. So basically, we indicate the strike, the deep angle,